From so simple a beginning, endless forms most beautiful and most wonderful have been, and are being, evolved. Charles Darwin. Please watch to the end. The most interesting part is at the very end. Lepetodrilus elevatus is a small deep-sea limpet belonging to the family Lepetodrilidae, best known for inhabiting hydrothermal vent ecosystems along mid-ocean ridges in the eastern Pacific. These environments are among the most extreme on Earth, characterized by total darkness, high pressure, rapid chemical fluctuations, and steep thermal gradients. Life here is sustained not by sunlight, but by chemical energy released from the Earth's interior. The shell of Lepetodrilus elevatus is low and cap-shaped, providing a streamlined profile that minimizes drag in turbulent vent flows. Unlike shallow-water limpets, its shell is relatively thin and lightweight, reflecting the reduced presence of shell-crushing predators in vent habitats. The shell's primary function is stability and protection against abrasive mineral particles rather than defense against predation. Lepetodrilus elevatus is typically found on hard substrates close to active venting, often forming dense aggregations. These clusters occur where chemical conditions are suitable for microbial growth. The limpet positions itself within narrow environmental windows where temperature and sulfide concentrations remain tolerable. Life is not a struggle for survival but a struggle for position. Carl Woese. A notable anatomical adaptation of Lepetodrilus elevatus lies in the structure of its gill and mantle tissues. These tissues exhibit an expanded surface area and dense vascularization, allowing efficient gas exchange in waters where oxygen levels fluctuate rapidly. This adaptation enables the limpet to remain active in zones that would be physiologically stressful for most marine gastropods. Feeding in Lepetodrilus elevatus is closely tied to chemosynthetic productivity. The limpet grazes on bacterial biofilms that coat vent surfaces, consuming microorganisms that derive energy from oxidizing reduced chemicals such as hydrogen sulfide. Rather than relying on a single food source, the species can exploit mixed microbial communities, providing flexibility in an environment where conditions change quickly. The muscular foot of Lepetodrilus elevatus is highly adapted for adhesion. It allows the limpet to maintain a firm grip on irregular, mineral-coated surfaces exposed to fluctuating fluid flow. This adhesion is essential for remaining within optimal chemical zones while avoiding displacement by sudden vent pulses or seismic disturbances. Reproduction involves the release of planktonic larvae into the water column. These larvae are capable of dispersing between isolated vent fields, an essential trait given the ephemeral nature of hydrothermal vents. When vent activity ceases, local populations decline, and recolonization depends on larval connectivity across vast distances. Ecologically, Lepetodrilus elevatus functions as a primary consumer within vent ecosystems. By grazing on microbial mats, it transfers chemosynthetically fixed carbon to higher trophic levels, supporting predators such as vent crabs, fish, and other invertebrates. Its presence contributes to the stability and productivity of vent communities. Lepetodrilus elevatus exemplifies a deep-sea survival strategy based on precision rather than tolerance. It does not endure extremes uniformly, but instead occupies narrow ecological niches where chemistry, temperature, and flow converge in just the right balance. Evolution is not about perfection but about fit. Stephen J. Good. If this changed your understanding of hydrothermal vent life, please support the channel. Like the video, subscribe, share it, and tell us in the comments which extraordinary deep-sea organism you'd like to explore next. Let's discuss in the comments.